Hello everyone, and welcome. Today we're diving into a fascinating area of mathematics called dynamical systems, exploring a paper by Lee Morales and Shin titled ** on the Plaque Topological Stability of Partially Hyperbolic Diffeomorphisms **. Now, in dynamical systems, stability is a huge deal. We're always asking, if we nudge a system a little, does its overall behavior stay pretty much the same? Think about a suspension bridge. If a small gust of wind hits it, we really hope it stays stable and doesn't suddenly start wobbling out of control. It's the same in math. We want to know if small changes to a system's equations lead to the same long-term patterns. For a class of systems called uniformly hyperbolic, the answer is a big yes. They are incredibly robust, but things get much trickier when we look at partially hyperbolic systems. These systems often aren't stable in the classic sense. This has led mathematicians to search for a new, more flexible idea of stability. That's exactly what this paper does, introducing a concept called Plaque Topological stability. Let's get into the basics. We're working on smooth, compact shapes, like the surface of a donut, with no edges. A diffeomorphism is just a smooth, invertible map from this shape back to itself. Now, this map is partially hyperbolic if at every point, we can split the space of possible directions into three types. There's a stable direction where everything gets squished, an unstable direction where everything gets stretched, and a center direction that's somewhere in between, not uniformly squished or stretched. The stable and unstable directions are well behaved. They bundle together to form what we call foliations. Think of them as layers, like pages in a book, that cover the whole space. But the center direction is the tricky one. It doesn't always form a nice, clean foliation. When it does, along with the other directions, we call the system dynamically coherent. This gives us a beautiful geometric structure to work with, a center foliation that helps us understand how points move around. Now, a classic result for simpler systems says they are topologically stable. This means if you tweak the system a bit, the new dynamics are essentially a slightly warped version of the old ones. Unfortunately, this beautiful property breaks down for our partially hyperbolic systems. We need a weaker idea that still respects the system's geometry, especially that all-important center foliation. This is where Plaque Topological stability comes to the rescue. The brilliant idea is to allow for some wiggle room, but only along the leaves of the center foliation. Think of it this way: instead of demanding that a point in the new system perfectly matches a point in the old one, we only require it to land within a small patch of plaque on the same center leaf. To make this precise, the authors use something called set-valued maps. Instead of mapping a point to another single point, these maps can send a point to a small set of points. The key is that this set must stay within a tiny neighborhood on the center leaf. This ensures our comparison respects the foliation structure. So, a system is plaque topologically stable if, after a small perturbation, we can find one of these set-valued maps that neatly connects the old dynamics with the new, allowing for those small shifts along the center plaques. In short, it's the perfect adaptation of classical stability, custom-built for the world of partial hyperbolicity. So what did the authors prove? Two major theorems. First, Theorem 5. It says that any partially hyperbolic system that is dynamically coherent and plaque expansive is also plaque topologically stable. Plaque expansivity is a technical condition, but it basically means that if two different paths stay super close in the center direction for all time, they must have been on the same center plaque to begin with. It's a property that's widely believed to be true for all these systems. So, this theorem says, assuming that conjecture holds, all dynamically coherent partially hyperbolic systems are plaque topologically stable. This is a huge result, drawing a direct parallel to the simpler, classic case. How did they prove it? They combined a few key ingredients: an adapted notion of expansivity, a shadowing property that also respects the foliation, and a general result showing that expansivity plus shadowing implies this kind of stability. Next, Theorem 6. This one tells us something about the structure of the dynamics. It says if a system is expansive and plaque topologically stable, then its long-term recurrent behavior in the center direction is completely governed by points that are center periodic. This means the most important dynamics happen on plaques that eventually return to themselves. This again mirrors the classical theory, where periodic orbits form the backbone of the entire system. Let's look at a few examples to see this in action. First, if we have a uniformly hyperbolic system, its center direction is trivial, it's just a single point. In this case, plaque stability is exactly the same as classical topological stability, so the new theory neatly includes the old one. A great second example comes from partially hyperbolic systems on the 3-torus. Imagine a 3D donut. It's known that these systems are both dynamically coherent and plaque expansive. Therefore, by Theorem 5, they are plaque topologically stable. This gives us a whole class of natural, non-trivial examples where this theory applies beautifully. Finally, the implications of Theorem 6 are profound. For any system that is expansive and plaque stable, we know that the heart of its dynamics, the recurrent part, is built from periodic plaques. All the complex long-term behavior is organized around these repeating structures. This gives us a powerful tool for understanding these complicated systems. So, to wrap things up, this paper introduces a brilliant new concept, Plaque topological stability. It masterfully adapts the classic idea of stability to the more complex world of partially hyperbolic systems by allowing for flexibility along the center direction. The main theorems show that under reasonable conditions, these systems are indeed Plaque stable, and that this stability forces the long-term dynamics to be organized around periodic structures. This provides a vital bridge between the well-understood world of uniform hyperbolicity and the wilder frontier of partial hyperbolicity. One fascinating open question remains. There is a small gap in understanding the relationship between different types of recurrent points in the center direction. If this gap can be closed, it would give an even sharper picture of the dynamics. In summary, Plaque topological stability offers a powerful and elegant framework for understanding robustness in these complex and beautiful mathematical systems. Thank you so much for watching. If you enjoyed this dive into modern mathematics, please give this video a like and don't forget to subscribe for more content like this. See you next time.